Okay, my name is Brian Lowe. I'm the president of Belleson LLC, and I'm here to talk about testing noise. We've got some regulators and a test setup, and I want to describe the way that we've done some noise testing on the bench. Uses some fairly sophisticated yet accessible test equipment. Number one, we're using a handy scope from Pi Engineering in Holland. It's this tiny little gadget up on the bench, and it feeds into the computer in through the USB port and takes some great measurements. It's a very accurate, very low level measurement instrument. It's got a 16-bit ADC in it, and it's got a lot of gain, so it's great for measuring noise. We're also using a custom-built noise measurement system, which really consists of a gain of 1,000 amplifier in 2 stages. It's running with full bandwidth of the amplifiers. It's using very low noise LT1028 op amps. If you know anything about them, you'll understand. They're set up with no band limiting, with the exception of the amplifiers themselves. So the bandwidth is approximately 230 kilohertz. So we'll certainly be able to see noise out to 200 kilohertz, even though, we could see noise out to 200 kilohertz, but the measurement system that we've got is only going out to about 100, which is good enough for our purposes. So the first thing I want to do is look at the measurement system itself and what the limitations are on that to make sure that it's good enough to measure the kind of noise we want to measure. Then we're going to look at the amplifier and see what that contributes to the bass noise. And then we're going to add the regulator to that to see what the noise is that's a contribution from the regulator. So both the scope, or the spectrum analyzer instrument, and the amplifier need to have significantly lower noise than the regulators that we're trying to measure. So that's the purpose of checking out the system first before we go and do the regulator measurements. So here we go. First, we've got this instrument running. I'm going to point the camera. I'm working as director and engineer and actor all at the same time. So this is the system that we're looking at to do the measurement. And you can see, let's see, I want to see if I can get this camera positioned so I don't have to stand here. Maybe I'll cut this out of the video. If not, then sorry. Alright, here we have the instrument that's fully functional and running, and you can see it's pretty ugly. We've got down about minus 110 dB right here. We've got some grungy stuff at around 35 kilohertz, and then some more at around 40 kilohertz, 42 maybe, and then some more stuff up here. If with that alone we would not be able to measure the noise levels in the regulators that we're trying to measure. In fact, one of the things that we can see as far as the sensitivity of this instrument, I don't know if you noticed, but we've got some fluorescent lights running here. I'm going to switch one off. Well, let me get off from in front of the camera. I'm going to switch off the fluorescent light, and you can see where a big chunk of that 35 kilohertz noise is coming from. And next, I'll switch off the overhead light, and that looks much better. Okay, now keep in mind this is measuring at the amplifier output, but the amplifier power is not powered on. So we can see that we're down around minus 120 dB all the way out to about 98 kilohertz. And so that's the baseline of the measurement instrument itself, the Pi handy scope. Now I'm going to be switching this light on and off a little bit just so I can make sure I don't plug something into the wrong socket. But next, I'm going to ground the input of the amplifier itself, still without turning on the power. This is the gain of 1,000 measurement amplifier. Okay, and I ground that, and I turn this off again, and you can see that the noise again is down around minus 120 dB, even less across a lot of that spectrum. Okay, now we turn on the power with that amplifier input grounded and see what the gain of 1,000 amplifier contributes on its own. That gives us something on the order of minus 90 dB across that same spectrum, except remember that we've got a gain of 1,000. So now with that gain, minus 90 is really not minus 90. It's minus 90 minus 60, because 60 dB is 1,000. So that's really minus 150 dB. So given that, we can certainly measure the noise in a regulator that's going to be on the order of minus 120 to minus 100 dB, or depending on the regulator, maybe minus 70 or 80. But at any rate, we've certainly got a measurement system that's clean enough and good enough to measure a very low noise device. Okay, I'm going to power off the amplifier and plug in place of a short to ground, I'm going to plug in an LM78 12. And then I'm going to power up the amplifier again, and we'll see the noise level on the LM7812. And sure enough, we can see what appears to be here some nice random noise. It's somewhere on the order of this RMS millivolts showing here. Remember, we've got a gain of 1,000, so RMS 100 millivolts actually turns into 100 microvolts. So we're looking at RMS voltage of roughly 100 microvolts across a bandwidth of about 100 kilohertz. And that's what we see on an LM7812. Alright, now we turn off the amplifier again. Okay, now I've turned the power off on the LM7812, and I'm going to plug in a Belleson SPZ78 at 12 volts, and we'll take a look at the noise on that. Now, I've seen this before, so I know how this is going to go, but I just want to show that we do comparative measurements by unplugging one part and plugging in another part, same test system, same setup and everything. So this is really some confirmation on the kinds of numbers that we put in our data sheet. Alright, I can get rid of that big spike at 35 kilohertz and turn on the amplifier. And we'll see what the SPZ78 at 12 volts is showing us for noise. And if you notice, the scope here is, the meter is showing us about 10 microvolts, which is 10 times less than the LM7812. You can also see, just by looking at the graph itself, the time plot, the oscilloscope screen basically, that we've got a very low noise level here. And you can see in the spectrum analyzer that the noise is going from about minus 110, because we're starting at 50, remember. So 50 minus 60 is, or minus 50 minus 60 is minus 110. So this goes from about minus 110 at low frequencies and decreases down to about minus 8. This would be what out here. This is out in the range of about 20 kilohertz here. So at the top of the audio frequency, we're looking at about minus 75. So minus 135 dB, and then that increases just gradually, just slightly, when you get out past 50 kilohertz and 60 kilohertz, but not a lot. So you can see that the noise levels here are very low, and the primary bulk of the noise is down in the very low frequency range. And that's our story on the noise. Let me back this up and say, I'll turn on the lights. And say thank you for watching. I'm going to give a quick close-up of the test amplifier just now, and then we'll say goodbye. And I'll turn on the noise-making fluorescent light again, and you can see, if we can get this focused. So there's the amplifier. It's got dual power supplies, one pair of power supplies for the measurement system and another pair of power supplies for the device under test. And here's the handy scope. I have to brag on it. It's been a very nice instrument. It looks fairly small and simple, but has a lot of capability. Until next time, from Brian Lowe at Belleson LLC. Thanks for watching.